Hello, this is a video on the concept of dissolving or miscible, which means do two substances, when they come together, do they want to stay together? The way in which you can remember it is like dissolves like, which means, first of all, I apologize, the scanned PDF is sideways, so and I can't rotate in the screen, so you're gonna have to print it out and write notes on it. So if you look, this page has sideways, and the other side of the page is just a place for notes. So how do you know if two substances come together? Well, since it's a physical process, it's most likely about intermolecular force. And the way we make you memorize it is, or remember it is, likes dissolve likes, which means if something has applies a Coulombic force to it, Coulombic force, partially negative, partially positive area, or simply a full positive like an ion, or a full negative, or an electron is considered a full negative. So if the two substances, solute and solvent, are like those, then they will dissolve in each other. The word also is miscible. Miscible means when two liquids do it. If they don't, they will not. So only nonpolar molecules will dissolve in nonpolar molecules or are miscible. Okay, so if you look at and the big reason, or the thing behind it, is substances with Coulombic force have regions or their whole substance that exert Coulombic force. And as you know, a positive, partially positive, or full positive thing will attract a negative thing, and two positives repel. So therefore, in a bucket of polar solvent, let's say like water, the partially negative ends, and this is the key phrase, the partially negative ends of one molecule are being attracted, forced to the partially positive end of another molecule. So they line themselves up, negative, positive ends, and there's a force between attracting them. So, and that's not true of nonpolar molecules. Nonpolar molecules, even though they have very, very small Coulombic force, it's not great enough to influence other particles significantly. So basically, they just sit there in a bucket, always moving, not interacting with each other. There's enough Coulombic force there to keep them together, but not enough to interact. So if I had a bucket of water, a polar molecule, and I could spin one of the water molecules, partially negative and partially positive end, all the other water molecules around it would spin also. That's not true of a nonpolar molecule. If I had a nonpolar molecule and spun it, it would not. All the other particles wouldn't really do anything. They just simply move around. So that's the first big thing. Okay. The first picture is basically showing the fact that to put a nonpolar solute into a polar solvent, you have to actually force the water molecules apart to put the nonpolar solute into that empty space. Remember, the other big part is that all solvent particles, this empty space in between it, and that's where the base particles or base units or particles of the solute go. So if you try to shove a nonpolar solute into a polar solvent, what will happen is it will go in, be forced in, but those two water molecules want to come back together due to their Coulombic force. So what will happen is, since the nonpolar solute particle doesn't have any Coulombic force, it's just getting pushed around by the polar polar solvents to try to get the two polar solvents together. So they push them away, and either they end up on the surface of all the polar molecules or on the bottom. Which one are they, on the surface or the bottom? That's due to the density. So this is so this one is polar solute dissolving in a polar solvent. So the big thing here, besides what we just said, is that sugar, the base unit or particle for sugar is a whole molecule, the polar solute molecule. It's a polar molecule. So when the water particles remove one of them, they don't break up. So in a solid sugar crystal, the solid polar solvent, they're just, the polar molecules are just really close to each other. And again, since they have a partially negative and partially positive end, they're lining up partially negative to partially positive. And what happens is the water molecules come up, the polar solvent come up, and they're attracted to, let's say, if it's the partially positive end of the polar solute, the partially negative ends of the water molecules are attracted to it. And then the other side of the polar solute, the partially negative end, the partially positive end of the water molecule are attracted to it. And don't forget that there's a bunch of other water molecules that are influenced by those water molecules. So they're pushing. So now it's a tug of war. And what happens is the water wins because there's more of them. So when they do, the water molecule, the sugar polar solute particle molecule, because it's not breaking up, is now by itself from all the other sugar polar solute molecules, and it's surrounded by water molecules. That's what is called hydrated. And since it's a polar solute, the partially negative ends have the partially positive ends of the water molecule near it, and vice versa on the other side. So if it's a partially negative end of the polar solute, it's the partially positive ends of the water molecule, and on the other side, if it's the partially positive end of the sugar polar molecule, it's the partially negative ends of the water molecule. Okay, and that's how things dissolve or are miscible for polar solutes dissolving in polar solvents. And of course, when can't you dissolve anymore? Well, when you run out of empty space. And also the other way of saying that is when you run out of water molecules that are influencing or surrounding the hydrated polar solute. We just say when you have no more empty space. So the other one is here. The other one here is an ionic solid. An ionic solid solute. For ionic solutes, the base unit is not a molecule; it's an ion. So therefore, the same exact thing happens, except with an ion, it's only one charge. So this sodium, looking at table salt, sodium chloride. So one of the sodium ions that is basically immersed in or close to water, since it's positive, it's the partially negative ends of the water molecule that's going to surround it. And remember that sodium ion is basically part of the salt because there are chloride ions all around it holding it together. So now again, it's a tug of war. And since there's more water particles, they win. So they pull off the sodium ion. And the sodium ion, as you can see, is surrounded by the partially negative ends of the water molecule. And of course, the same thing happens to the chloride ions, but chlorinized, but it's the partially positive end of the water molecule. Again, they are called hydrated ions. So, and then the last one, of course, is when they don't. When you take a non-polar solute and try to add it into a polar solvent, or vice versa, and you just, as we saw here, what happens is the non-polar solute goes in, and these two water molecules will want to come together due to the Coulombic force, and it squirts out. The only other thing that is possible is a non-polar solvent and a non-polar solute. And what that is, and I didn't draw a picture, is you basically have two particles that don't really influence each other. So basically what you have is you have a true mixing where they just basically moving at all times, and they move in the volume until their randomness makes them evenly mixed. So that one, there is no interactions. They just mix by randomness. So that's the three. That's the major ways of looking at how things dissolve. Okay, polar solutes and ionic solutes dissolve in polar solvents. Non-polar solutes dissolve in non-polar solvents. Okay. The other things are I talked about the two important issues with polar solutes dissolving polar solvents. The molecules stay as themselves; they don't break up, and then the hydrated molecule, since it has a partially negative and partially positive end, the water molecules are affected different. Which end's closest to the molecule is different depending on which end the polar solute molecule end you have. And that's what that says. And then this one here is talking about the empty space, the fact that that the solute base particle goes in the empty space. This right here, these three types of solutions, we'll talk about later. Thank you.